Welcome to the Problems Channel Season 2, Episode 35, the episode which I titled A Regular Polygon Recognition, because in this episode we will solve a mathematical problem in which we are asked to recover precisely the shape of a mystery regular polygon on n vertices named a1 through an if we are given a relation across the distances between the vertices of the said polygon that has the following shape known ahead of time. The reciprocal of the distance between the mystery polygon's vertices a1 and a2 is representable as the sum of the reciprocal distances between the vertices of the mystery regular polygon a1 and a3 and a1 and a4. Under the constraint specified, we're asked to recover the value of n. Before we deep dive into the underlying mathematics, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, think about the information that we present in that episode, and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In order to make sure that we're all on the same page, in the mathematical problem S2E35, we're given a mystery regular polygon on n vertices named a1, a2, a3, and so on, an, where n is a, let's say, non-negative whole number. And we're told that the distances between the vertices of this mystery regular polygon obey the following given and known ahead of time relation. The reciprocal of the distance between the vertices of the mystery regular polygon a1 and a2 is representable as the sum of the reciprocal distances between the vertices of the mystery regular polygon a1 and a3 and a1 and a4, and under the constraint specified, we're asked to recover the value of n. What is n is the question of the mathematical problem S2E35. As I was preparing this episode, I looked around to see how other people solve this problem, and it turns out that other people use trigonometry, which then they reduce to a cubic equation that has some interesting shape. I didn't even look at it. X cubed equals 0. They managed to solve this cubic equation and obtain the correct answer. But unfortunately, in my time, for example, if you were to solve this problem using trigonometry, which you then reduce to a cubic equation, you will get exactly 0 credit for solving this problem, because if you use trigonometry, which you then reduce to a cubic equation to solve this problem, then you fail to think like a mathematician, you fail to think out of the box. And the whole idea of working on this particular problem is precisely to develop your ability to think out of the box and to nurture your ability to think like a mathematician. A way in which you will solve this problem that will lead to a full credit for the solution of this problem essentially boils down to the combination of the eliminate and conquer problem solving approach, which is precisely the approach whose mechanics we're studying right now, and the so-called Ptolemy's inequality or Ptolemy's equation. So how do we solve this problem in a way that will lead to us getting a full credit for it, and how do we think out of the box, and how do we think like a mathematician when we address this problem? Well, overall, we first to begin eliminate the elimination rounds, because the eliminate and conquer problem solving approach prescribes that first we lasso in all our suspects. And in this case, what are all our suspects? Well, our initial pool of suspects, or we build the elimination process precisely on n. And n in this case will begin with a non-negative whole numbers, which have the following shape: 1, 2, 3, 4, 5, and so on. Now, let's talk about n equals 0, what is going on in this case. When n is equal to 0, then essentially we have 0 vertices and 0 sides to our mystery regular polygon on n vertices. And n equals 0 corresponds to the empty set of regular polygons. So essentially we have nothing to do, and we eliminate number 0. When it comes to the numbers 1 and 2, some people in the audience will say, Roman, look, 1 gone and 2 gone as regular polygons is basically a nonsense. These are degenerate polygons if they even exist. But to the enlightened members of our audience, I would say that yes, definitely in a few seconds we will eliminate n equals 1 and n equals 2. But in the grown-up mathematics, there exists this happy family of the so-called finite dihedral groups, Dn. Dn, we actually met the finite dihedral group D4 in the previous episode when we were discussing how to fill out a 3x3 magic square. Remember when we said that once we construct one 3x3 magic square, we automatically get 7 more isomorphic images of that parent magic square? Well, this is precisely the dihedral group D4, comes from the happy family of the finite dihedral groups Dn. There are several ways to define these groups through the so-called defining relations. And one such relation says that Rn, where R is the rotation of the underlying regular polygon on n vertices precisely, is the same thing as reflection squared, is the same thing as R times f squared, which is equal to the identity of the group. And this defining relation basically says that if we take a regular or a non-degenerate regular n-gon on n vertices, we have precisely that many rotations of the regular polygon about its center, let's say counterclockwise in the parent plane, by 2 pi over n radians consecutively. F squared is the reflection, and the order of that element is 2. So that means that 2 consecutive reflections in the same axis of symmetry of a regular polygon results in the identity. It restores the regular polygon to its original shape. And then this relation over here says that if we reflect a regular polygon in one of its axes of symmetry and then execute the smallest congruence rotation, do it twice in a row, will also restore the polygon to its original. Bottom line over here is that the interesting groups D1 and D2 can actually be worked out, obviously, purely algebraically, but it is possible to come up with a regular polygon with one side this time for the group D1 and a funny looking regular polygon on 2 vertices with the sides that curve like this, and explain geometrically the degenerate, let's say, dihedral group, finite dihedral group D2, which is actually sometimes called a quadratic group. But in our case, evidently, we throw out the numbers 1, eliminate numbers n equal 1 and n equal 2, and now we consider the n equals to 3 case. But we are told, evidently, the largest number that we see in the naming of the vertices of the mystery regular polygon is what? It's A4. That means that there are at least that many vertices, 4, and 3 is less than 4 if we have a regular polygon that has 3 vertices and 3 sides. The names of its vertices run A1, A2, and then 3, and then they stop. There is no A4. Consequently, because evidently 3 is less than 4, we eliminate number n equals 3. And in other words, we eliminate an equilateral triangle or a regular trigon from consideration in this problem. What is the next regular polygon? The next regular polygon is n equal to 4. That corresponds to a square. And let us say we have a square with the size, with the length of its side a. And what does this relation mean, or how does this relation across the distances between the vertices of the underlying Mr. Regular polygon translate into the world of squares? Well, that is quite evident. Let's say we'll do it over here. Let's say this will be A1, this vertex is A2, this vertex is A3, and this vertex is A4. How do we render the given relation for a square with the side length of A? Well, the distance between the vertices A1 and A2, such vertices belong to one and the same side of a square, will be what? 1 over A. That must be equal to what? The distance between the vertices A1 and A3, it is this guy. And what is this? This is the side scaled by the square root of 2. So 1 over A square root of 2 plus, what is this? The distance between the vertex A1 and A4, A1 and A4. This will be 1 over A. This is still A. And what do we have now? Now we have a mathematical absurdity, because in this relation over here we have nothing but strictly positive real number, and this strictly positive real number is the same as this strictly positive real number. So now apparently what we have is one and the same real number can be represented as what? A given strictly positive real number is the same strictly positive real number plus yet another strictly positive real number. What is this? This is an absurdity. This does not happen. Even if we go like this, for example, multiply this equation through by A, obtain 1 and 1 cancel out, square root comes over here. What does this imply? This implies the square root is equal to 1, squaring both sides. The function of square root we know is monotonically increasing and is continuous. 2 equals 1. This is again an absurdity. This is how we eliminate n equal to 4. And what does that mean? That means that the only next viable customer, so to speak, is a regular polygon on n vertices, or A. Precisely, the next customer is a regular pentagon or a regular polygon on 5 vertices, because in this case the vertices of a regular polygon will be named A1, A2, A3, A4, and A5. 5 evidently is greater than 4, so now at least we have some hope with the given relation, or at least, to put it pedantically and correctly, with a regular pentagon we do not have any immediate straightforward ways to eliminate a regular polygon on 5 vertices or a regular pentagon, again because 4 is less than 5. We have 5 vertices, so maybe the relation shown over here can work out for a regular pentagon. And here is precisely the essence of why this problem should have been solved that way. The folks who have solved this problem using trigonometry, which they then reduce to a cubic equation, have failed to analyze the given relation as a mathematician would realize the given relation. And what does it mean for a mathematician to analyze the given relation? Well, remember that mathematics, first and foremost, is a play of thought, which is a process of generating and regenerating and combining and recombining mathematical ideas. If we simply took the given relation and bluntly and blindly flipped it into the underlying trigonometry and then squeezed the cubic equation out of it, we fail to think like a mathematician. We fail to analyze the given relation as a mathematician. And how would a mathematician analyze the given relation? Well, I have said it many times. I'm about to say it now, and I will say it many times in the future. There is more to mathematics than meets the eye. And what does that mean? That means that even if we are given a relation shown over here with how many summands? 1, 2, 3, only 3 summands. It does not mean that what we see is what is really going on under there. Maybe this relation has 5 instead of 3. Maybe it has 5 summands or 5 terms, and the last 2, let's say, cancel each other miraculously and happily precisely due to the specific property of a specific regular polygon. Or maybe there are not 5 but 7 terms which also happen to cancel each other happily, or maybe there are 9. That's one way to think about it. The other way to think about the given relation is as follows. How many summons? 3. And how many distinct distances does this relation capture? Well, this relation captures 3 distinct distances. The distance between the vertex A1 and A2, the distance between the vertex A1 and A3, and the distance between the vertex A1 and A4. But again, there is more to mathematics than meets the eye. There is more to mathematics than meets the eye. And maybe what we have over here in reality, not 3 distances, but how many? 6 distances. And if these distances are sprinkled across these 3 fractions or 3 ratios in such a way that they cancel each other out in each fraction or in each ratio, then instead of 3 distinct distances, we may very well have 6 distinct distances. And what relation, or more or less famous or perhaps standard relation, that connects 6 distances in geometry are we aware of? Well, in its most general case, that will be the Ptolemy's inequality that establishes a certain relationship between 6 distances in the plane. In a specific case, the Ptolemy's inequality becomes the Ptolemy's equality or the Ptolemy's theorem. In order to establish the common ground for the upcoming solution of the mathematical problem S2M37, recall that the so-called Ptolemy's inequality establishes a particular relationship between the 6 distances across any 4 points that are located in one and the same ambient plane. And the 4 points at hand are, let's say, the points A, B, C, and D. In their most general position, it is not the case that all 4 points will belong to one and the same circle, but as a separate exercise, it can be shown that any 3 distinct points, A, B, and D, for example, in this case, belong to one and the same circle. And in this case, I show over here on the left-hand side of your screen such a circle. The points A, B, and D belong to that circle, and the point C does not. In that case, it can be shown that the inequality shown with this arrow right here, the strict inequality shown with the white less than sound, holds for the following distances. The distance between the points A and C, the cross distance, so to speak, the diagonal of this non-degenerate four-gon, times the distance between the points B and D, which is another diagonal of this quadrilateral ABCD. So this is 1, 2, 2 distances. The product of these distances is always strictly less, in this case, than the sum of the products of the following distances. Between the points A and B times the distance between the points C and D. So this is 3 and 4. And the distances 5 and 6 are what? The distances between the points A and D shown over here, and the distance between the points B and C shown over here. Thus, we count 1, 2, 3, 4, 5, 6. In general, in the most interesting case, 6 distinct distances that are generated by 4 distinct points that belong to one and the same plane. The case when the fourth, or let's say all 4 points, belong to one and the same circle shown over here, that case, and that case only, generates the equality. The equality I show over here with yellow chalk over here, and the arrow points to equal to, so this product is equal to the sum of this product. Only in the case when all 4 points sit on one and the same circle, this relationship becomes the Ptolemy's equality, or the Ptolemy's theorem, if you will. And for the curious travelers, it turns out that if we remember that 3 distinct points, any three distinct points define what? Any three distinct points define a unique plane. That means that 4 points are under no obligation to belong to one and the same plane. So in that case, if the points A, B, C, and D are not coplanar, in other words, we step out from 2 space into the 3 space, then the Ptolemy's inequality holds as well in 3 space. Now, I will not be proving the Ptolemy's inequalities and equalities in the theorem, but as mathematically inclined thinkers, we should always be happy to jump on the opportunity to generate a clever, interesting, and insightful proof. But for now, in order to keep the size of this episode manageable, we will take that the Ptolemy's inequality, Ptolemy's equality of the Ptolemy's theorem hold true, and we'll take that fact at its face value. And this is precisely the analysis that you were expected to carry out and the idea that you were expected to generate in order to get a credit for the solution of this problem. Now we take the Ptolemy's theorem or Ptolemy's equality and apply it to our regular pentagon whose vertices are named A1, A2, A3, A4, A5. And in this regular pentagon, we select the following quadrilateral: A1, A3, A4, A5. We know that all these vertices sit on the parent circumcircle in this case, and our quadrilateral A1, A3, A4, A5 is cyclic. All the vertices of this quadrilateral belong to one and the same circle, and we simply write down the Ptolemy's equality or the Ptolemy's theorem for that cyclic quadrilateral. So what will we have? We will have on the left hand side the product of the distances between the points A1 and A4 and A3 and A5. So we write A1, A4 times A3, A5 is equal to what? The product of the sum of products of the distances between the points A1 and A3. A1, A3 times what? A4, A5. A4 and A5 plus the product between the of the distances between the points A1 and A5 times A1, A5, A3 times A3, the distance between the vertices A3 and A4. That much is understood. Again, instead of inequality, we use precisely the equality, the Ptolemy's theorem, applied to the cyclic quadrilateral whose vertices are precisely a subset of the vertices of a regular pentagon. Now we go back to our given relation, and what do? Well, we construct a product. Let me write it down maybe over here so that you can still see it. The product P will be what? Precisely the product of the distances between the points A1 and A2 times the distance between the points A1 and A3 and times the distance between the points A1 and A4. This is the product. You see why this product? This is precisely the distances that were given in the constraining relationship in this problem. So the distance between the points A1 and A2 times the distance between the points A1 and N3 times the distance between the points A1 and A4 applied to this case. Now let us carefully do precisely that. Let's divide this relation through by this product. On the left hand side, what will we have? We will have the distance between the points A1 and A2 times the distance between the points A1 and A3 times the distance between the points A1 and A4. On the left hand side, we'll work on the other guys later. What do we see over here? Well, the distance between the points vertices A1 and A4 and A1 and A4 canceled out mechanically instantly because these are basically one and the same distances. Now, what else do we see over here? Let's analyze the distance between the points vertices A3 and A5 and the distance between the points A1 and A3. What can we say about these two distances? Well, these two distances are actually one and the same in all non-degenerate regular polygons on n vertices. Why is that? Well, the distance between the vertex A3 and A5 skips one vertex, vertex 4. In other words, to get from A3 to A5, if we were to walk over the periphery of the parent circumcircle, we'll first see the point, the vertex A4, then we will arrive at the vertex A5, and conversely, if we travel from the vertex A5 to the vertex A3, we will visit the vertex A4, but the distance A5, A3, and A3, A5 is precisely the same as the distance between the points A1 and A3, because again, this distance hops over, so to speak, through this vertex A2 of our regular pentagon, and that relation will hold for any regular polygons on n vertices which are non-degenerate, precisely because all the vertices of such a regular polygon are what? All the vertices of a regular polygon, not degenerate polygon, are sprinkled over the periphery of the parent circumcircle, uniformly displaced one from each other, the immediate neighbors, but the same angular measure 2 pi over n. Consequently, let me use maybe another chalk over here, cancel out the distance between the points A3 and A5 and the distance between the points A1 and N3. This will hold, again, this relation, the equality of these distances will hold for any non-degenerate regular polygons. Also, it will hold in a regular pentagon. And what will we have left on the left-hand side of this relation? You see, we will have 1 over the distance between the vertices A1 and A2 on the left hand side. Now let me erase a little bit of the material, maybe prepare some, make some room for the manipulation with this guy and with this guy. Actually, you know what, we can do it over here. Let's do this. Let's work on this summon right here. In the numerator, we'll have the distance from A1 to A3 times the distance from A4 to A5 over, remember we're dividing this Ptolemy's equality through by the same product. So we will have what? The distance A1, A2 times the distance from A1 to A3 times the distance from A1 to A4. What can we say over here? Well, the distance from A1 to A3 and A1 to A3 cancel, they cancel each other out without much thought. And what else can we say? Well, the distance between the vertices A4 and A5, that is the distance between two immediate neighbors over here. And what is the distance between the points A1 and A2? Exactly the same thing. It's the distance between the two immediate neighbors, A1 and A2. And what can we say about such distances in any non-degenerate regular polygon? Exactly, these distances are one and the same. So in other words, in this case, we cancel out the distance between the vertices A4 and A5 and the distance between the vertices A1 and A2. Now, I'll take a little bit of time to erase some of the material and prepare it for the fight with the less summoned over here, but you already see what is going on, right? Here, on the right-hand side of the equal sign, we manufacture what? 1 over what? Distance between the vertices A1 and A4. And now we just have to fight it out with this guy, the distance between the vertices A1 and A3 in our given relation, and we will do it in the next segment. Very well, in the previous segment we applied the so-called Ptolemy's equality or the Ptolemy's theorem to a cyclic quadrilateral whose vertices are a subset of the vertices of a regular pentagon, A1, A3, A4, and A5. And by doing so, we generated the left-hand side of the original relationship that we're given in this problem, the reciprocal of the distance between the vertices A1 and A2 of a mystery regular polygon, which is equal to the sum of the reciprocal of the distance between the points vertices A1 and A4 of a mystery regular polygon, and what else? The sum shown over here divided through by the product shown over here. I wrote it down for you so that you can see it in one convenient location. And the question now is, can any of the distances in the numerator and the denominator of this ratio be canceled out? And the answer is yes. Some distances can be canceled out. And which distances are those? Well, the distance between the vertices A3 and A4, like in this case, for example, A3 and A4, is what? Is one and the same as the distance between the vertices A1 and A2, A1 and A2. And that statement holds true for any non-degenerate regular polygon, precisely because the angular displacement or the linear distance or the distance over the minimizing geodesic in a given space. This is Euclidean space. The minimizing geodesic is the straight line. The straight line distance between any two immediate vertices of any non-degenerate regular polygon is one and the same. So now these guys are different, but let me show it with red chalk, cancel out this distance and this distance. Now what do we have left? Now we have left in the numerator the distance between the vertices A1 and A5, in this case of a regular pentagon. And in the denominator, what do we have? A product of the distances between the vertices A1 and A3 and A1 and A4. In this case, in case of a regular pentagon, can any more cancellations be carried out? No, these distances are prime, so to speak, or co-prime. Nothing else can be factored out. The distance between the vertices A1 and A5 is one thing, and the distance, in some sense, that distance is equal to the length of a side of a regular pentagon. And sometimes we can think about such side as a degenerate diagonal, but in this case, in the denominator, we have what? The distance between the vertices A1 and A3 and A1 and A4. In these guys, these distances are genuine non-degenerate or traditional diagonals in this case. And what do? Well, instead of copying this ratio verbatim, we copy it in a very clever or suggestive way. Remember, in the given constraint, what do we have? The reciprocal of the distance between the vertices A1 and A2 is represented as the sum of the reciprocal distances between the vertices A1 and A4 and what? A1 and A3. So now we write it down precisely like that. 1 over the distance between the vertices A1 and A3 times, what is this? The distance between the points A1 and A5 over the distance between the points, the vertices A1 and A4. You see, we rewrite this ratio, this fraction, if you will, in this particular way. And what do we conclude from this observation already? What kind of next fruitful tactical maneuver would you carry out? What does this relation mean if we juxtapose or reconcile it against the given relationship? Put this video on pause, think about it. We'll answer that question in the next segment. In terms of an if P then Q implication, that means that if the given constraint applied to the distances across the vertices of the given Mr. regular polygon does hold, that means that this factor over here must be 1, and that means that the distance between the points A1 and N5 and A1 and A4 must be what? Must be 1 and the same. I will use the grown-up notation of the letter D for distance to underscore the importance of this conclusion, to render it as follows. The distance between the points A1 and A5 then must be equal to the distance between the points A1, again, 1, and A4. And what does that mean? If the distance between the points A1 and A5 and between the points A1 and A4 is one and the same, then that means that the triangle A4, A1, A5 is what? The triangle is isosceles. Let's write it down. The triangle A4, A1, A5 is isosceles, with the distances obviously A1, A5, and A4, or the lengths of the sides A1, A5, and A1 and 4 being one and the same. And what does that mean? How would you answer that question? If the triangle A4, A1, A5 is isosceles with the lengths of its sides A1, A4, and A1, A5 being equal, that means that all three geometric objects that emanate from the vertex of this isosceles triangle, the point A1, are actually what? Are actually one and the same object. Let me use maybe this reddish chalk. The height, the median, and the angular bisector that emanate from the point A1 all coincide, all coalesce into one object, but that means that the height, that is also the median, cuts the base of this isosceles triangle or the line segment A4, A5 into two equal parts like so. And what does that mean? Well, observe that the line segment A4, A5 is the base or the proverbial base of the isosceles triangle A4, A1, A5. It is also a side of a mystery regular polygon on n vertices, but we know that each and every vertex of a non-degenerate regular polygon sits where? Sits on the parent circumcircle. That means that the line segment A4 is also a chord. Let me try to somehow portray this semicircle halfway realistically. That means that the line segment A4, A5 is a chord of the parent circumcircle. And now what do we have? We have a chord of a circle that is cut into two equal parts, just to make sure that maybe we have the differences between this with three dashes. We have a chord of a circle divided into two equal parts by a straight line, that is the height of this triangle, and that implies what? Via Euclid's Elements, Book 3, I'll write it down for you over here, guys, maybe let's say in blue. Book 3, Proposition 1. Book 3 is where Euclid develops the theory of circles. Via Book 3, Proposition 1, due to Euclid and his elements, that means that when a straight line cuts a chord of a circle in half, that means that that straight line precisely contains the center of that circle, let's say the point O. And what does that mean? If the height of our isosceles triangle A1, A5, and A4 contains the center of the parent circumcircle, that means that that height plays the role of a diameter of that circumcircle. And what does that mean? That means that because the vertex A1 of a mystery regular polygon on n vertices sits on one extremity of this diameter and no other vertex of the regular mystery polygon sits on the other extremity of that diameter, evidently because there are no opportunity to squeeze more vertices between the vertices a4 and a5. 4 and 5 are two immediate neighbors in the set of whole positive numbers. You cannot stick in any other whole positive number between 4 and 5. That means that the number of vertices of our mystery regular polygon must be what? The number of vertices of a mystery regular polygon must be necessarily odd. And what does that mean in our case? In our case, it means that we will have exactly as many vertices on one side of this diameter as on the other. But since we have the vertex number A4 on this side of the diameter, that leaves the choices for what? That leaves the choices for let's say A2, and somewhere here, let's say A3 on one side, and A6, and somewhere A7, on the other side. And that precisely means that the answer to the problem posed in this episode is what? Let me write it down in red, somewhere here. N is equal to 7 precisely. That is the answer. N is equal to 7, and the mystery polygon is a regular heptagon or a regular polygon on precisely 7 vertices. And we should be able to show that for any value of n that is odd but that is greater than 7, for example, for the values of n that are, let's say, 9, 11, 13, 15, and so on, this conclusion will not hold. In other words, the distance between the points A1 and A4 and A1 and A5 will not be the same anymore. Why is that? Well, we saw that when n is less than 7 in a regular pentagon, we had the points 4 and 5 were located which way? Let's see, we had A1 here. This was, I know it's too small, but you guys can go back to your records, and A3, A4, and A1, A2, 3, 4, and 5. They were located, the points A4 and A5, they were located on one side of the diameter of the parent circumcircle, but these distances could not possibly work out to be the same. Here, in this case, the vertices A4 and A5 are located on the opposite sides precisely of the diameter of the parent circumcircle, and for all the other values of n greater than 7, 9, 11, 13, 15, and so on, what will happen? The vertex A5 and A4 will again squeeze to this side. So let's say our diameter partitions the parent plane into two halves, let's say the right half plane and the left half plane. So for all n odd and greater than 7, 9, 11, 13, 15, and so on, the vertices of the corresponding regular polygon on that many vertices will be what? They will all live on one side, let's say in the right half plane in this case, and there is no way it can so happen that this relation, the distance between these points, will be one and the same. Thus, no trigonometry, no cubic equations of any kind, just a straightforward manipulation of middle school material. But if you want to engage in some more symbolic manipulation, then we can actually show with an equation, if you will, that the answer to this question in this problem must be 7 as follows. What is the magnitude of the central angle generated by any two immediately adjacent vertices of any non-degenerate regular polygon on n vertices? what is the magnitude of the angle, for example, A4OA5, this one? Well, that magnitude is apparently is what? 2 pi over n. And now let us consider, for example, the triangle A1, O, and A4. By what well-known nice theorems can we proceed further? Using which theorems we can proceed further? Well, the magnitude of the central angle in the magnitude of the corresponding angle in the circumference. That's one of the theorems actually that Euclid proves in his Elements in book 3. What can we say about this magnitude? Well, the magnitude of the central angle is twice the angle in the circumference. That means that this angle over here, this angle, let me write it down this way, it will be what? That angle will be half of this angle, so that will be pi over n. But we already proved that our height, in this case shown in red, of the isosceles triangle A4, A1, A5 is also what? Is also the bisector of the interior angle at the vertex A1. It means that this smaller side over here, let me write it down here, I'll show it here. This smaller angle is what? Is precisely 1/2 of this angle, so it will be pi over 2n, where n is the mystery number to recover. Now, because the point O is the center of the parent circumcircle, and the line segments O, A1 and O, A4 play the roles of what? Of the radii of the parent circumcircle. These distances are the same. In other words, I'll put 1 dash and 1 dash. The triangle O1, O, and A4 is what? Isosceles by Fameris Pons Asinorum, Euclid's Elements, Book 1, Proposition 5. The magnitudes of the angles at the base, this angle right here and this angle right here, are what? By magnitude, they are precisely the same. So what do we write by the corresponding theorem that Euclid proves in his Elements in Book 1? The magnitude of the interior angles of any non-degenerate planar Euclidean triangle is pi. And what does it mean in our case of the isosceles triangle A1, O, A4? Well, that means that the magnitude of this smaller angle here, let's say O, A1, A4, is what? Pi over 2n plus another pi over 2n plus what? Plus the magnitude of the central angle shown over here, this guy, the large guy, the angle A1, O, A4. What can we say about the magnitude of that angle? Well, that angle is assembled from 3 central angles, evidently. We already proved that. We proved all the nice conclusions that the number of the vertices in this mystery regular polygon must be odd. A4 is equidistant diameter-wise from the point A5 and so on. That means that the central angle A1, O, A4 is assembled from 3 central angles that are what? Pi over 2n. 2 pi over n each. That means what? 6. 3 times 2 is 6. 6 pi over n. This is our equation. And what do we have here? Pi is canceled out. We have 1 equals 1 over 2n plus 1 over 2n plus 6 over n. 1/2 n plus 1/2 n will be what? 1 equals 1 over n plus 6 over n. Multiply this equation through by n uniformly. What do we have? N equals 1 plus 6 equal to 7. The answer is one and the same. N equal to 7. The regular heptagon is the answer to the mathematical problem S2E35, and there was a method to my madness of breaking up all the conclusions and what does that mean and what does that mean in a series of small segments. And the method behind that madness is the following. Many people, many students who are still in college will not, and apparently are not able to solve this problem this intended way. They all rush immediately into trigonometry and cubic equations. Oh my God, what is happening? And not that many people can actually generate this line of reasoning that is minimalistic in some sense, or as simple as possible, but not simpler. And precisely that is exactly the type of reasoning that we want to master how to craft on this channel. And what does this experiment tell us? This experiment tells us in mathematics, when it comes to mathematical reasoning, there exists some mysterious secret source that transcends the nature of the underlying objects. In other words, this secret source in the mathematical reasoning works in the same way when it is applied to middle school material of isosceles triangles, heights, points, circumcircles, and so on. And it works in exactly the same way, amazingly enough, it works in exactly the same way when it is applied to grown up, for example, way to automatically generate automorphism group of any given group G. And this is precisely why we go through these exercises on this channel, because in the grown-up setting, when you will be defending your or constructing, making your PhD in mathematics happen, you will use precisely the same creative juice to glue together the material under investigation in your area in exactly the same way, in which we created a construction, in which we created a proof of for the solution of the mathematical problem S2E35. In this episode, in other words, we reasonably creatively manipulated nothing but the middle school material of isosceles triangles, heights, circumcircles, and so on, instead of using the blunt force of trigonometry and cubic equations. This is it for the mathematical problem S2E35, and we will move on to a new challenge next. Our next challenge, the mathematical problem S2M38, will be the last problem that we will use for a dedicated study of the eliminate and conquer problem solving approach. In that problem, we're given a planar triangle ABC with the following additional data. The point M is chosen on the side of the triangle CA, and the point N, as in Nancy, is chosen on the side of the triangle CB in such a way that the distance from the point C, from the vertex C of this triangle ABC, is one and the same to the points M and N. In other words, the length of the line segments CM, M as in Mary, and CN, N as in Nancy, is one and the same. Also, in this triangle, the line segments AN and BM intersect at the point O. The line segments AN intersect and BM intersect over the point O, such that the distance from the point O to the vertices of the parent triangle A and B is again one and the same. In other words, the length of the line segment OA is the same as the length of the line segment OB. And lastly, we're told that the magnitude of one of the interior angles in this triangle is given ahead of time, known. It is, let's say, alpha sub 0. This magnitude is known, and the challenge in this question, in this problem, is to recover the magnitudes of the remaining two interior angles. Again, to underscore, just to make sure that we're all on the same page, this is not a typo, this is not a mistake, this is apparently the intention of the author of this problem. Which one specific angle, interior angle of the parent triangle ABC, whose magnitude is alpha 0, is not told to us. It could be, in theory, anything, and under these conditions, the challenge is to recover the magnitudes of the remaining two interior angles of this triangle. Like I said before, this problem will be the last problem that we use for a dedicated study of the eliminate and conquer problem solving approach. And even though in general, yes, this problem can be solved in any which way, the intended solution that you should try to generate should plow directly through the eliminate and conquer problem solving approach. Good luck. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the mathematical problem S2M38.